Inverse relations. Also, this is a concept you learned in grade 11. We need to work with inverse relations in order to solve for a different variable. A simple example is the difference between finding out how much money you'll earn if you work 15 hours, as opposed to already knowing how much you need to earn, but kind of working backwards to figuring out the number of hours needed. So the inverse of a function is the reverse of the original. It undoes what the original function has done. This was the big one we talked about in grade 11. So the blue one is the parent function parabola, and its inverse is the square root, the plus or minus square root. So see the plus or minus in front there. So when we calculate the inverse equation here, we would get a positive or negative square root. So every point on here, let's say the point 2, 4 is right there on the blue one. That means on my inverse, I'm going to take that coordinate 2, 4 and flip it. 4, 2 is on my inverse, is on the red one. So every x becomes a y, every y becomes the x. That's why we have a reflection in the line y equals x. So if this were a mirror right here, and if I had kind of painted this blue line with some kind of wet paint and folded it here, I would end up with this reflection right here. So it's a reflection through the line y equals x, because that's what the inverse function does. The graph of the inverse relation is a reflection of the original in the line y equals x. So here are some of our other parent functions. So the red one here would be the radical function, possibly. It's been compressed a bit, and then this is its inverse. So all of these, any of these graphs here are inverses of the other. Oh, so it's labeled the blue one is the original, so it's not a parent function. It was probably parent radical that got shifted over a few units, but it's got the point AB on the blue function. So on its inverse, it's going to have the point BA. They just get switched. So these are just kind of examples. Not all of these graphs represent functions. So this notation is only used if it is a function. So on this whole screen, you should see that there are two red graphs that are not functions, two inverses that are not functions. This is one, and this is one. And a way to quickly test for that is with the vertical line test. So if I drew a vertical line straight down through, I'm drawing on the upper parabola one here. If I drew a vertical line anywhere through here, it's going to cross twice. So it fails the vertical line test. It fails the vertical line test. That means that the red one's not a function. The way you can check that if you don't have it is if you go back to your original and you draw a horizontal line. If your function fails a horizontal line test, then the inverse is going to fail the vertical line test. So if I look at this, I'm going to look at the second one down here. If I draw a horizontal line through the blue one, there's nowhere I can draw a horizontal line through the blue function f of x where it's going to cross twice. It's always going to cross once. So since it passes the horizontal line test, I know that its inverse will pass the vertical line test. So here's our first example. We're going to find the inverse equation here, the algebraic inverse. And so I've got some steps there for you. The first step is to interchange x and y. Well, when I look at my equation, I don't see a y there. So let's switch out the f at x for y. Y equals negative 2x cubed plus 6. Now I can interchange x and y. I'm on this step here. So I'm going to put an x here, negative 2y cubed plus 6. The next step says follow SAMDEB. So to follow SAMDEB, that's the opposite of BEDMAS. That's BEDMAS in reverse, because when we're isolating, which is what we're doing here, when we're isolating, we do it in the opposite order. So when I'm isolating, the first thing I'm going to do is the subtraction, addition, subtraction. So the first thing is to subtract 6 from both sides. That gives me x minus 6 equals negative 2y cubed. Okay, here's sometimes a point where students get stuck because they're not sure, do I divide by -2 or do I get rid of the exponent 3? So let's look here. We already did subtraction and addition. We did that. The next step is multiplication and division. So that tells me I have to do the division before the exponent. The exponent is second last. So I'm going to do the division next. So I'm going to divide both sides by -2. And I can either write it like this, dividing by -2, or I can put it all as one, put them separately, divide by -2 like this. So what I have now is, remember negatives can't go in the denominator, so I'm going to move the negative up, -x over 2, and then I have two negatives here, they'll give me a +3, equals, these two are gone, and I have y cubed. So now I'm at the last part of, last piece, which is to find the third root. Third root of both sides. So I'm going to put a radical sign here in the 3, third root, and a radical sign over all of this stuff, and a third root. Now before I continue on, I'm going to do a little aside here. If I had x squared equals 16, then we would take the square root of both sides, square root of x squared, square root of 16, and we would have x equals, except here I'd have a plus or a minus. So I would get plus or minus 4 because 4 squared is 16 and -4 squared is also 16. So I need a plus or a minus. Do I need a plus or a minus on a third root? Okay, let's think about that. Plus or minus on a third root. So look over to the right here. I have some space over here. What if I had x cubed equals 8? Okay, I'm going to take the third root of both sides, the third root of x cubed, and the third root of 8. So these cancel out. I have x equals, the third root of 8 is 2. Now, should that be a plus or a minus 2? Let's see. 2 cubed gives me 8, and that's what I had originally, right? 2 cubed is 8, so that's good. Is -2 cubed also 8? No, -2 cubed is -8. So when we have a third root, we do not do the plus or minus. The plus or minus is not needed when we have a third root or a fifth root. Anytime this exponent is odd, we're not going to do a plus or a minus. We're only going to have one answer. So just to show you one more time, if I had x cubed equals -27, so the third root of this side, the third root of this side, so I'm left with x equals, the third root of -27 is -3, and that's the only answer. I can't have x equals +3 because +3 times +3 times +3 is not -27. So when you have a third root, we're just going to stick with the sign that was in the original question, whether it was a positive like the 8 or a negative like the 27. So back up to my original question in the red and green here. I'm going to rewrite that as the third root of, and -x over 2 could also be written like this with -1/2 x if you like, plus 3. It doesn't matter. These are the same. You don't have to change it. And that's equal to y inverse. So we have found the inverse. Now the next thing we have to talk about, or that we have to consider here, is this piece up here at the top. Is the inverse a function? That's what we're trying to decide here, is the inverse a function. So how do we know if this is a function? Well, a function means you put in one number, you get out one number. For every input, there is one and only one output. So if I put in a number for x into my answer here, if I sub in some number for x right here, will I get one answer out or two answers out? I will only get one output. I'll only get one answer. So this is a function. It's a function because I didn't do the plus or minus. If I did the plus or minus, I would not get a function because I get two answers every time I sub something in. So this is a function, so I can also use the notation f inverse at x. Looking back up to this graphic at the top here, this is the parent cubic function. So the parent cubic function, I just said it is a function, right? This is a function, and its inverse is over here. This is the inverse of it, and you can see it's also a function. It passes the vertical line test. Anywhere you draw a vertical line, it's a little confusing in here. It's a little hard to see. You have to take my word for it, but if you did draw a vertical line right down the y-axis, it would still only cross once. It would cross at 0, 0, because here horizontally on the original, it's only crossing at 0, 0. It only crosses once. So is the inverse a function? Yes, it is, and that's why we're allowed to use this function notation right here. Down at the bottom, the graph is, let me switch to the highlighter. This is the graph of the inverse. Okay, that's what you're looking at right there. What is its end behavior? Is it continuous? So I've provided a graph here for you. I just graphed that on Desmos, which I think you have some homework to do where it says using a graphing calculator. Just use Desmos. Let me put some arrows on here. Desmos doesn't do that. One drawback of the program as of now anyway. What is the end behavior? So what's going on at the ends here? Let's start over here on the left. As our x values approach negative infinity, these are my x, this is my x-axis here. So as my x values are getting more and more negative, what are the y values doing? What is the graph itself doing? The graph is slowly but surely getting higher. So my y values are approaching infinity. On the other side of my graph, on the other end, I've got as x approaches positive infinity, what are the y values doing? What is the graph itself doing? Is it going up or is it going down? It's going down very slowly, but it is going down. So way off to, if our x values are way over at infinity, if we've got an x value of 1 million, right? If our x value is way at 1 million, our y value is going to be a lot lower. So our y values are approaching negative infinity. And the last thing that this question has over here on the right-hand side is it continuous? Is our graph continuous? So remember what that means. It means that there's no asymptotes or holes or anything that would stop, that would force you to lift up your pen and put it back down again if you were drawing it. So is it continuous? Yes, this is a continuous function. This is our next slide and our last one. Absolute value. At this stage, we are only finding their inverses graphically. So what I mean by that is we're not going to switch x and y and calculate as we did in the previous example. We're not going to determine its equation algebraically. We're just going to look at it graphically. So the first thing we have to do is graph this function, h at x. This is absolute value function. First thing you want to do is, well, we've got to put a scale on here. We don't have a scale in our grid. And when I look, how do I get an idea of what scale to use? Should I count by 2s, 5s, 10s? Look at these two numbers right here, and they will help you to envision where the vertex will go. What we'll do, since we haven't done absolute value for a little bit, I'm going to start with the parent function here. So I'm going to draw the parent function on first. The parent function is y equals the absolute value of x. So just to review that with you, some coordinates on it. Absolute value means everything that is inside the absolute value brackets become positive. So if I sub in a -2, whoops, if I sub in a -2, once I put that in, it's going to come out as a +2. All negatives become positive, and all positives stay positive. So 3 stays a 3, 0 stays 0. So this is a V shape, and it is very linear. It has it is completely linear on either half. It's like a line bent in half. So let's put a scale on here. So I've just placed my scale in here. I'm counting by ones, but I only labeled every second one because it's a bit crowded here. I've got my x-axis and my y-axis. So I'm just going to first start by graphing this one here. I don't need to graph very many. I don't need to put a whole lot of points on because I know that it's linear. There are two linear pieces. So I've got 0, 0. And then another one that I kind of calculated up there was 3, 3. So that's there. I really only need these two because I know it's a straight line, they'll connect, but I'm also going to have, for example, 6, 6, 7, 7, 8, 8, 1 half, 1 half, 2 fifths, 2 fifths. Those are all there. On the left side, it's the same. I've got -2, -2, putting a point there at -2, -2. I've got -4, -4, -18, -18, -5, -5. So just put a few on there. It's probably one of the easiest parent functions to graph. And then draw a straight line with your ruler connecting those dots. Now with the tablet that I'm using a Wacom tablet, it will read the ruler and it will skip. So it'll be hard for me to draw with a ruler. So don't do what I'm doing. Actually use a ruler, draw a straight line. Okay, that took an unreasonably long amount of time for me to do. So now we're going to graph the first bullet, graph the function h at x. So this has a vertex of 5, -2. Same setup that you would see if you had a quadratic. The vertex comes from the d and c values. So 5, -2, I put a dot there. I have no other transformations. There's no a value, so it's not stretched, it's not vertically flipped, nothing else. So I can, if I wanted to, I'm just going to put the graphs right on, the points right on here. You could sub in if you needed to. So for example, you could sub in x. So here's h at x equals absolute value of x minus 5. Straight line -5 -2. Let's say I sub in a 1. I'm going to get absolute value of 1 minus 5 minus 2. So h at 1 is going to be absolute value of -4 minus 2. Absolute value of -4 is a positive 4. So we get 2. So we're going to have the coordinate 1, 2. That's one way to do it. Let me put that on here, 1, 2. But that's really long. I don't want to do it that way. All I really need to do, because all I need to know is that there are no other transformations. So it's going to have the same shape, exact shape as my red one, which means my new vertex right here, if that were the origin, I would be going from here, I would be going over 1 and up 1, over 2 and up 2, over 3 and 3, right? So I'm just going to do it that way. For my vertex, I'm going to, I'm counting from my blue vertex. If I count over 3 to the right, then I've got to go up 3, and then I put my point there. So all of these points are exactly the same. So I'm just going to draw 2 more straight lines. Okay, I clearly gave up on my ruler. This is the transformed function. The only thing that happened is we took our parent function, we moved every point 5 units to the right, and we moved every point 2 units down. So that's pretty straightforward to draw. And of course you should use a ruler. Do as I say, not as I do here, right? This is not good. That was the first part, graph the function. The next bullet says state the domain and range of h at x. So the domain and range of h at x. So the domain for the absolute value function, so h at x domain is x is an element of real numbers. There is no restriction on what we can sub in for x into this equation right here. We can sub in, for x, we can sub in anything we want, positive, negative, decimal fractions, square root, anything, no problem. That's the domain. So how about the range? You can see by looking at the graph that the range is limited. Remember, the range is the vertical distance, the vertical space that your graph takes up. So this graph is going down as low as -2, but it's going up from there to infinity. So our range is y is an element of real numbers, right? We can still sub in real numbers such that all of the y's that we sub in, or all of the y's that we will use, not sub in, all of the y's that we will see in our graph are all greater than or equal to negative 2. Those are all the y values utilized by this graph, by this function. The third bullet says graph its inverse on the same set of axes. The first thing I'm going to do before I graph the inverse is I'm going to draw in the line y equals x, because the line y equals x is the line of reflection. So it might help me to make sure my graph looks like it's been reflected correctly. So I'm going to put in a black dotted line. Y equals x is wherever x and y are equal to each other. So for example, putting a dot right now on negative 4, because that negative 4, my y value equals my x value. Negative 8, my y value equals my x value there. 0, 0, 1, 1, 6, 6. So it's actually going to overlap the red part here. So I'm going to put on 4, 4, for example. So it's going to overlap my original graph a little bit, but I'm going to draw a dotted line right through the line of reflection. So there's the line y equals x. You would use a ruler, of course. That is our line of reflection. So the next thing we need to do is graph the inverse. So to graph the inverse, I'm going to take the points from my blue function here, like 5, negative 2, and I'm going to switch them. They're going to go to it's going to go to 2, negative 5, that point. So every point that was on my original function gets switched. So 5, negative 2 goes to negative 2, positive 5. I might have said that backwards. So negative 2, positive 5. The signs don't switch, just the numbers switch. 5, negative 2, I said negative 2, 5. If I could put a dot there. There we go. Negative 2, 5, that's going to be my vertex. And then I can pick another point that I have. Let's say I look at this one here. I have this point here, or we actually calculated one over here on the left. So 1, 2, that's going to be flipped over, and that's going to go to 2, 1. This one that I put the circle around is 8, 1. That was on my original. That's going to go to 1, 8. So you just need to get a few points and switch them around, and you have enough to do your inverse. So I'm going to try and draw that on with a ruler first, and if I can't, I will have to just do it free. So there in purple is my inverse. Now I can tell clearly by looking at it, it's not a function, so I'm not going to call it h inverse at x. I'm just going to call it h inverse because it's not a function. It fails the vertical line test. The second last bullet says state the domain and range of our inverse. So our inverse, domain and range. Domain, remember the domain and range. So, okay, look at our domain, look at the picture. It's the vertex, the furthest to the left we go is negative 2, and then it goes off to the right from there. So all the x values, x is an element of real numbers, such that the graph will utilize everything from negative 2 and then to the right. And of course, in case you forgot, the range of the function becomes the domain of the inverse. The domain of the inverse becomes the range of the function. So I don't even need to think about the range. I'm just going to go up here and look at my domain, and I'm just going to rewrite it, but I'm switching the x with a y. So once you do the domain and range for one, then you have it for the other. You just have to remember to switch it. The last bullet says, is the inverse a function? So we already talked about that. Is the inverse a function? No, it's not. If not, restrict the domain and or the range of the original function. So go back and look at the blue one, at the blue graph here. What you do is you go to the vertex and you cut it in half. I'm going to start at my vertex here at 5, negative 2, and I'm going to essentially erase either the right half or the left half, and it doesn't matter which one. So my domain, I'm now going to change my domain here, my restricted domain from the original, restricted domain, so always going back up to the original, is now x is an element of real numbers such that I'm only going to take the right side. So x is greater than or equal to 5. So my function is now only valid on this right hand side here. I'm just kind of making it a little more bold. And of course it's not going straight, but let's pretend it is going straight. I'm only using this part right now of my graph. The other part is gone. So if our original graph was only that really thick blue piece, then of course my inverse would be a function because there's only a line. So I have restricted the domain of my original to create an inverse that is a function once I do that. So now I have a function. Now I can call it h inverse at x. So that's kind of messy, but hopefully you can figure it out there. For your homework, read through these pages and make more notes. Your textbook has great examples, so read through the examples, make more notes to yourself. There's text correction there. You will find practice questions on these pages here, and of course check your answers. When you have to graph, you're going to use the online graphing. Desmos is the best one. Well, I like it best for your online graphing. That's it.